Okay, hello everyone and welcome back to your YouTube channel. And welcome to this very amazing video. As you must be aware, I am teaching a course about frequency stability and control in modern power systems. And in this course, we have many practical examples. And today we are working with the example number 6. We are building the knowledge, and you must remember that in the previous example, we have been working with the primary frequency control. And today, example number 6 is it's building on top of that. Today, we will start with the classical low frequency control. To be honest, we are working with the secondary frequency control. Today, we are implementing the automatic generation control. Well, without further delay, let's move forward, okay? Let's move forward, and the first thing that I would like to tell you is that all the opinions and all the comments here are just my responsibility, okay? And also, all this teaching material will be available at ResearchGate. For that reason, I highly suggest and invite you to visit my ResearchGate repository. Also, the files, the Simulink files and MATLAB files will be available at my GitHub repository. If you are watching this video, it's because you are in YouTube. Feel free to subscribe, feel free to leave a comment, or anyway, you can send me one email and I will be extremely happy to help you, okay? And finally, if you're interested to know what we are doing in the lab and many other things about research and industry collaborations, please go to Twitter and LinkedIn and subscribe over there. Before we start, just a very short overview about frequency control, okay? All of you already know that when we have an under frequency event, the frequency goes down. I mean, when we have a generator outage, we have a deficit of generation. As a consequence, the machines slow down and the frequency goes down, okay? And for that reason, we have what we call the primary frequency control. The primary frequency control is basically a controller, and the objective is reestablish the balance between generation and demand. As a consequence of reestablishing that balance between generation and demand, the frequency, the pseudo-steady state frequency, usually is below the rate frequency. For that reason, we have a secondary frequency control, and the objective of that controller is sending back the frequency to the rate frequency, okay? And here in this slide, you can see the two different controls, okay? Here we have the synchronous generator. Inside we have the inertia response, and here we have the governor. This control loop is basically acting on the prime move of this synchronous generator, and this is the primary frequency control. The reference is coming via telecommunication system, and in that telecommunication system we can define those reference, okay? And the secondary frequency control is basically sending the signal to this communication system. One of the indicators of the operation of the secondary frequency control is the area control error, okay? And here you can see the most used controller. This is a PI controller to define the settings, okay? Well, if you remember in the previous practical sessions, specifically in the example number 2, we create the system, we create a test system, one area with a primary control. You must remember on the left-hand side, you can see the block diagram. Here we have the inertia. This is the transfer function to replicate the behavior of the system inertia. Here on the top left, you can see the frequency-dependent loads and the rotating mass loads. And highlighted here in red and orange, you can see this is the controller that is dedicated to define the mechanical power going to the machine, okay? This is basically the primary frequency control, or what we call the turbine dynamic control. In this case, we are using a classical first-order transfer function, and this is the time constant related to the turbine dynamics. On the right hand side, you can see the implementation. We use the classical Simulink models. To be honest, there are two files in the GitHub. One of them is dedicated to the basic block diagram, and the second one has all the details about the parameters used here, okay? One of the things that you must remember from that example is that when we run a load increase, the frequency decrease and there are some oscillations, okay? You can see that the governor is doing the job. When we have a sudden load increase in blue color, you can see how orange try to follow the blue line. In this case, the mechanical power is trying to follow, and it will follow at the very end the load change. However, what is the bad news here? That because the objective function of this controller is basically reestablishing the balance between generation and demand, and also we have here a constant that is called droop, the steady state frequency will not match the rate frequency. What I'm telling you is that at around 20 seconds here, you can see that the frequency is still below the 50 Hertz. And that is the reason that we need to work with the secondary controller. Well, this is the example today. Today we are implementing the example number 6, and it's basically one area with AGC. On the left-hand side, you can see this is the example number 2 that we already implemented. In this system, you can see that the input here is the set of the mechanical power. But in this case, we assume this a constant, okay? But today we are adding here a control loop. In this control loop, we have here what we call the frequency bias. With them, we are calculating the ACE. From there, we are going to the PI that is creating the signal for creating the reference for the governors. What I'm telling you is that this area highlighted in red-orange is basically what we call the AGC control loop. And the idea of this control loop is basically creating a signal for those governors in order to recover the frequency and try to minimize the frequency deviation after the disturbance. Okay, now it's time we want to implement this inside Simulink MATLAB, and that is the job. The job right now is that we will implement this using Simulink MATLAB, okay? What I will do now is I will allow you to create step by step following my video. I speed up the video in order to save time, but at the end you will be able to create the system. If you want, you can use a functionality from YouTube to reduce the speed of the video, and you can see slowly how to create the system. Okay, now in front of you we have the final Simulink implementation. This is the dynamic model, or the model to assess the frequency response of a single control area with AGC, Automatic Generation Controller. This is the controller that we have been discussing. You can see here they are very specific area. Here we have the power load change, and here we have the inertia block. Here we have the first order transfer function for the governor, and we add this control loop over here to represent the AGC. I intentionally include this manual switch. When the switch is on the position here below, at the bottom, you can see that the AGC is disconnected. And the idea is that right now I want to run a couple of time domain simulations. I show you the impact of having a AGC inside a single area system. Right now, the position of this manual switch is in such a way that we don't have AGC. I will run 900 second simulation. And the first thing that you can notice is after 900 seconds, the frequency is presented here. And this displays 49.92. That is below the right frequency. But let's see the plots, okay? In this scope, we have 4 signals over here. The first one at the top is the frequency. Then we have the ACE. Then we have the load change, and here the mechanical change, okay? As you can see in a steady state, as I say before, the frequency is not matching the 50 Hertz. In fact, this frequency is 49.92. However, let me do the following. Let me take a zoom here around 100 seconds, okay? What you can see is that I use a 400 megawatts load change. And when we include this load change, the governor is doing the job, is trying to increase the mechanical power to follow the load increase, okay? As a consequence, you can see here the frequency, but the frequency is reaching in a steady state a frequency that is below the right frequency. In this case, 49.92. What is the solution to recover the frequency? Well, right now, let's switch on the AGC, and now let's run the simulation. Now we are running the simulation, and after we run 900 second simulation, you can see that the frequency is 50 Hertz. Here you can see that after 900 seconds, the frequency recovers and goes back to the right frequency. But let's see the details here. That is where the thing starts to be interesting. Because as you can see, we use the same load change, 400 megawatts. And you can see how the frequency goes down, and there are some oscillations over here. But before 100 seconds, the AGC is kicking in. And the AGC is identifying that there is a ACE. I mean, there is a area control error, and the controller starts to change the reference of the governor. And what is the consequence? The beautiful consequence here is that after the under frequency event, several seconds after that, the AGC kick in and the frequency goes back to 50 Hertz. That is the beautiful part here, okay? And as you can see, that implementation was extremely simple. It was extremely simple and very simple for us to follow. Well, this is the end of this video. I would like to say thank you to all my students in frequency stability and controlling modern power system. This is all for example number 6. In this example, we create a single area control system, and including the primary frequency control, the turbine dynamic and governor, and also in this very specific video, we add a control loop, a secondary frequency control loop, that is the AGC, the automatic generation controller. Well, that is all for this video. Thank you very much for watching, and I will see you at the next one. Thank you. Bye now.